Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone, welcome back to one of my lectures on nuclear magnetic resonance spectroscopy. Today is part 6. Let me start the lecture by asking you to draw the proton NMR spectrum of diethyl ether. You will draw the structure and then submit the structure to any of the program you use, or you can calculate it manually using the table as we mentioned in the previous lecture, or using the charts to get approximate value. Here the program is showing the methylene proton at 3.48 and the methyl protons at 1.21. Remember that these two methylene protons are equivalent, and the CH3 protons are equivalent to one another. We can say via C2x of symmetry. From the previous discussion, you are probably under the impression that a typical 1H NMR spectrum exhibits just one signal for each proton nucleus, and the same thing is true for the carbon 13. So you will end up by drawing the spectrum this way. Well, that's wrong. This is not right. What we observe is actually this type of spectrum with fine structure. We call this first order spin-spin coupling. For the unexpected lines in NMR spectrum, look at the multiplicity of the signal equal to the number of lines in the signal. So multiplicity of this peak, we have one peak, two, three peaks. The multiplicity of the methyl signal is triplet. Give it T. Triplet. The multiplicity here for the methylene, 1, 2, 3, 4. The multiplicity of methylene is quartet, 4 line, quartet, Q. And the space between the line of the multiplet called spin-spin coupling, J constant. Give it J constant, spin-spin coupling. But what call this? Mechanism of nuclear spin-spin interaction. There are two pathways of magnetic interaction, what we call coupling, occurring between nuclei A and X with non-zero spins. Either direct interaction, what we call a dipole-dipole coupling. Based on the theory of the electrodynamics, the energy of the interaction through space between two nuclear dipole moments, mu1 and mu2, associated with two nuclear spins, is given by E equal K mu1 mu2 3 cosine 2 theta minus 1 divided by R to the power 3. K is constant, R is a distance between the two magnetic nuclei, and theta is the angle between them. In a solid, this direct dipole-dipole interaction energy is found to be considerable. However, in fluid like liquids and gases, because of random tumbling motion of the molecules, the average value of 3 cosine 2 theta minus 1 becomes 0 and the value of E vanishes. So, in liquids and gases, this is no direct nuclear spin interaction. There is no direct nuclear spin interaction. Number 2, indirect and scalar coupling, spin-spin coupling J. In liquids and gases, the interaction between two nuclear spins is transmitted through the electrons of the chemical bonds that intervene between them. This is called indirect spin-spin coupling J. Let's see. If we have homonuclear proton, we have CH3 and CH2. CH2, these two protons can adopt 2 to the power, because they are number 2, 4 orientations. One of them, that the two spins of this nuclei will be against opposing the V naught. One is down, one is up, one is up, one is down, and 2 going up. Here will be -1 magnetization. Here is 0, and here is 1. This will raise up the B net a little bit higher and will show up at higher frequency. This is 0, so nothing will happen. This is against, so it will decrease the energy and decrease the frequency. The probability here is 1, probability here is 2, and probability here is 1. So we'll find this triplet in 1 to 2 to 1 ratio. Alright, that this CH3 will be splitting by this CH2 to a triplet. But what happens to the methylene signals as a consequence of the 3 neighboring methyl group? How many spin states can 3 equivalent hydrogen adopt? Draw all possible combinations. What multiplicity do hydrogen predict for the methylene signals? What will be the intensity ratio of lines? I'm looking now for how this CH2 appear under the influence of the effect of the CH3. Again, number of orientation 2 to the power n means 2 to the power 3, so are expecting 8 orientations. The 3 will be against, 2 against, 1 with, 2 against, and one with B naught. Now, two with one against, two with one against, two with one against, and thus probability will be 3 with. That's one orientation, and 3, 4, and 3, 7, and 1, 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 orientation. The magnetization here, minus 3 over 2, minus half, 3 by 2. The probabilities would be 1, 3, 3, 2, 1. So the quartet will be of these intensities. Quartet, 4 lines, 1 to 3 to 3 to 1. And how to draw it? We draw this, and J between lines are the same. J value, this is equal to this, J value, this is J value, okay? And how this is, and to measure the signal, delta will be in the middle. This is delta for this peak. The spin-spin coupling checklist. Are both nuclei magnetic? Are they non-equivalent? Are they separated by 3 or fewer bonds? بمعنى صح لازم يكون النيوكلياي اللي بتعمل كابلينج مع بعضها لازم تكون spin active، لازم يكونوا non-equivalent، they are separated by 3 or fewer bonds. Here is an example. Which hydrogen in the structure below will show coupling to each other? HA and HB bond 2, 3. The bond between them 3, so we are expecting coupling. A and C 1, 2, 3, 4. A and C, the intervening bond 4. We are not expecting coupling. HA and HD 1, 2, 3, 4, 5. 5 bond, no coupling. B and C, B and C, bond 2, 3. Yes, we are expecting coupling. B and D 1, 2, 3, 4. No coupling. C and D 1, 2, 3. Yeah, we are expecting coupling. G and D 1, 2. Oh, doctor, these two are equivalent. Even though it's 2 bond, but since they are equivalent, we are not expecting coupling. We are not expecting coupling. Remember, N hydrogens can generate only n plus 1 different spin states from 2 to the power n spin combination. For this molecule, HA will be coupled to HB. As we mentioned before, that's 3 bond between them. There is coupling. So here is 1, n plus 1 will be 2. So I'm expecting A to couple by B and show as a doublet, 2 lines. Indeed, HA coupled to HB and show 2 lines in 1-to-1 intensity ratio, 1-to-1. HB will split by HA and by HC, 3 bond and 3 bond. So we have here what we call J3 AB and J3 BC. Okay? And the information suppose for the moment that AB is higher than BC. Okay? Then B will split by A to a doublet. And then each line of this will split by C to another doublet. So how many lines we have here? 4. But 4 in 1-to-1-to-1-to-1 ratio. We call it doublet of doublets. We call it doublet of doublets. 4 line in 1-to-1-to-1-to-1 ratio. Now, how would you describe the appearance of HB if the two coupling J3AB and J3BC were accidentally equivalent? So B will see A and C equivalent. So N will be 2 plus 1 equals 3. So it will be triplet 1-to-2-to-1 ratio. Right. HC will be split by both HB and CH3. And remember that CH3 3D. Okay? Now suppose that J3BC is higher than J3CD. C is higher, then it will be just only 1 plus 1, 2. Doublet. Now, we have 3 HD. 3 plus 1 is 4. So each line will be 4. Quartet. 1 to 3, 3 to 1. 1, 3 to 3 to 1. And what we will see is doublet of quartets. Doublet of quartets. How would HC appear if J3BC was less than J3CD. So HC will be coupled with 3HD first, so you will get a quartet in 1 to 3 to 3 to 1 ratio. Then each one of these lines will be coupled with HB as a doublet, so you get 1, 1, 3, 3, 3, 3, 1, 1 ratio. This we call it quartet of doublets. Quartet of doublets, QD. But if these two coupling, JBC and JCD, it happen to be equivalent, so HC will see the 3HD and HB equivalent. So HC will see like its neighbor 4 equivalent, 4 plus 1, 5. And then you will see 5 lines. We call it quintet. We call it quintet with relative intensity 1 to 4 to 6 to 4 to 1. If there is a simple way to summarize it, yes, if a nucleus is coupled to another n nuclei with half I, and all coupling constant are equal, the signal for the nucleus will be split into n plus 1 lines, whose intensities ratio can be predicted from Pascal triangle. إيه هو Pascal triangle? Let's say if we have 0, we'll have only one signal. If the neighbor nucleus just only one nucleus, okay, go to the right and right one, go to the left and right one. So it's 1 to 1, and we call it doublet. Now, the neighbor 2 nuclei from the above, 1, go to the right and right one, 1 plus 1, 2, so in the middle right 2, and then to the left 1, so it will be 1 to 2 to 1. 3 nuclei, go to the right, right 1, then 1 and 2, in the middle between them, right 3. 2 and 1, in the middle, right 3. And then right 1. So, if you have 3 neighbors, it will show up 4 lines in 1 to 3 to 3 to 1, and that's quartet. If you have 4 plus 1, so I'm expecting 5. Here is 1. Go and write a letter on right hand 1. Between the 1 and 3, sum them, it's 4. 3 and 3 in the middle, write 6. 3 and 1 in the middle, write 4. Sum them, okay? And then 1. That's how to write Pascal triangle. For a spectrum to be first order, عشان تظهر زي ما احنا بنقول كده ان التريبلت تظهر تريبلت في لاين 1 to 2 to 1 والكوارتت تظهر 4 lines 1 to 3 to 3 to 1. لازم يكون الدلتا the frequency between the chemical shifts of any pair of nuclei must be much larger than the value of the coupling constant. يعني بنحسب بالهرتز الفرق بين التو لاينز. يعني مثلا كان عندنا هنا مثل وكان عندنا اثل. in hertz الفرق بينهم في التردد دلتا ميو divided by الجي value اللي بين التو لاينز. لو كانت أكبر من 10 higher than 10 then we are in the first order spectrum. First order spectra exhibit the following. Spin multiplets are centered in the resonance of the frequency. يعني لو أنا عايز أجيب بالظبط البيكة دي دلتا فين، أقول بالظبط في النص هنا بالظبط بين التو دول، يبقى هنا يبقى الفريكونسي سنترد بالظبط في النص. السبيسنج between adjacent component of the spin multiplet اللي هي جي، هلاقي ان الفاليو بين هنا وهنا هي زيها قد بالظبط دي قد دي قد دي قد دي. Multiplicities that result from coupling exactly reflects n+1 rule اللي هي for I equal half. اوكي، اللي هي احنا قلنا الايه الكابلنج اكزاكت ريفلكتد مالتيبليسيتيز. يعني ايه؟ بنقول دي جنبها 2 يعني تطلع تريبلت، دي جنبها 3 تطلع كوارتت. الانتنسيتيز بتاعت السبين مالتيبلتس برضو corresponding to the coefficient of the binomial expansion given by Pascal triangle اللي هي احنا قلنا ايه 1 to 2 to 1 triplet 1 to 3 to 3 to 1 quartet etc. If the nucleus coupled is not sets of I equal half the total multiplicity L. انا عندي بقى ان هو مش زي بعض، النيوكليوس هي I equal half بس النيوكليوس بتختلف ايه عن بعضها. يعني مثلا هنا 3 دي 3 زي بعض بس عندي واحدة بي، هنيجي نقول يبقى ال HC جنبها 3 دي and 1 B L equal 3 plus 1 times 1 plus 1 يبقى 4 times 2 is equal 8 and we have a 8 lines 1 2 3 4 5 6 7 8 lines. The nuclei with the same chemical shift do not split each other even when the coupling constant between them is non-zero. Once they are chemically equivalent, they are not going to split each other and show that in the spectrum. Finally, describe the condensed format of the spectra of diethyl ether. How do we record that in report? We had the spectrum. How we record it in the notebooks or in publication? You write proton NMR. Let's say what instrument you are using, 400 megahertz. The solvent, write the solvent, and then the first peak 1.22, it's triplet. J in hertz between the peaks is 6.94, and that's belong to 6 proton for 2 methyl. This is the first peak. Second peak 3.49 quartet. J value, you can subtract this from this or that from this. Any two Okay, or make the take the average of these differences, you'll find again it's 6.92. Since they are coupled to each other, JAB equal to JBA. So the value between the difference here is equal to the difference in here. Okay? And that's for 4 proton, and it belongs to 2CH2 group. Okay? Hope you found this lecture useful. See you in part 7 coming soon. Bye bye.